All right. So last week we went over chapter 1. Okay, mostly. Like there are still a couple sections of chapter 1 that we're gonna cover later on. Okay, about the proof techniques. Okay, but now move on to chapter 2. Right. These are the topics for today. So we can go like quite fast as well, because they are quite the ones that you know, right? Mostly. Okay. So that this chapter is about basic structures, including sets, functions, sequences, summation, and matrices. Okay, we are focusing more on like binary matrix. Let's see the first one. Hold on. This one, set. So that let's have an overview of about sets. Right? We know that a set, right, consists of a number of members, elements, or objects. Right? So we use a symbol like shown here, like A, smaller a. We use the lowercase letters for members of the set mostly, and the capital letter for the name of the set. So we can see like examples here, a set of all words in English alphabet, A, E, I, O, U. There are 5 members in the set. The second example is about a set of positive integers, less than 100. So the minimum would start with 1, right, positive. So 1, 2, 3, up to 99. So there are 99 members in the set, right, less than 100. Okay. We could have duplicate members in the set. But when we count the members or elements in the set, we just only count the unique ones, right? So that in this example, 1, 3, 3, 4, 5, 7, 7, then the members would be just 5 of them. Okay. The set could have an unorder of the members, right? We can put any member first, second, next. Okay, they are still the same set. When we have a lot of members in the set, and we can use like this symbol, right? This one, ellipsis, to represent like the remaining members in the set, like here, set of English alphabet, A, B, Z, D, E, up to Z here. Okay, so the set, the universe of the set, or like could be, have to be identified explicitly, right? If it's about English alphabets, or like positive integer or negative real number or something else. Okay, so that we can find the number of elements in the set. Let's see some symbols here, okay, that would be used in this course, okay, the capital N stands for natural numbers, or like integer could be 0 as well, just like when we count objects, 0, 1, 2, 3, and so on. The capital Z, that's about integers. If we have the plus sign on the top, right, superscript, so that means positive integer. Okay, R stands for the real numbers. R plus, that's a positive real number. So that's not include 0, okay? C is a complex number, and Q is for the rational number. Okay, so what is a rational number? A number that can be represented as just like x, right, divided by y. Otherwise, the number is irrational, right? Irrational number. So in Thai, what is it? Takkaya, atakkaya, right? Okay. The properties of the set, right, can be defined like this. Okay, as we see here, like set of the set S, okay, consists of members where members X, where X is a positive integer less than 100 or something like this. Okay, so that the properties would be those that are listed here. Moving on to the next one about the interval notation. They are similar, but actually they are not. Okay, they look similar. So we have to be very careful on this one. Okay, just like a bracket or something here. So the first case, this one, okay. First case, okay, represent a number that is starting from A, okay, and to B, right? Let's say like 0 to, okay, okay, like this. So that means like the X, right? X, where X could be greater than or equal to 0.5 and then less than or equal to 3.2. But if the notation is different, like in the second case, okay, this one, okay, means like open interval, partially open interval, so that the sign here is different. X is less than B. Okay. If we have the sign here, so that means X is greater than A. If we have open interval like this, that means X is greater than A and less than B. Oh, I'm sorry. What happened? Okay. This one, right? So we have a closed interval and open interval, partially closed or partially open, like in the second and the third case. Okay. What else about the set? Universal set. We use the symbol U for universal set, and for the empty set, we use this symbol, right? Or this one, symbol. Empty set. Empty set. Okay, that the set with no member. So that at the right-hand side, you can see that a Venn diagram, right, can be used to represent a set, right? Any set. Here is a set of English vowels having 5 members, so that the universal set here, that's about set of English alphabets. Okay, some of them are the English vowels, right? Right? We can have many different elements in the set, like in this example, like some elements are numbers, some are letters, okay, or like capital N, that's a natural number. This is a integer. This is a rational number and irrational number, something like that, or real number. Okay, this could be members in the set. And we know that, okay, this is an empty set, right? Right? We can write it this way or the other way, but this one is, the next one here is different. It's a set of empty set again, right? Okay. Then when we have multiple sets, okay, starting with 2 sets, right? They are equal if and only if they have the same elements, right? Number of elements are equal, and all the elements that belong to set A are also belong to set B. For example, this is equal set, the left and the right hand side, or this one, second case as well. They are all equal, right? A equal to B. This could be A. This could be B. And then we have subset, right? Subset. We have this, remember this sign, this notation. It means that A, set A, is a subset of B. Right? That means every members of A belong to set B. Okay. We can use the right quantifier to represent the requirement for the subset here. Like each member is X for all the members. X is a member of set A, then X is also a member of set B. Okay, so that is related to what we discussed last week. Okay, so that I may skip some detailed information because they are quite straightforward, and then you can also look at that by yourself too, okay? When set A is equal to set B, right? A equal to B, it means that A is a subset of B, and B is also a subset of A. Okay, with the quantification here, for all x, okay, x is a member of A, then x is also a member of B, and vice versa, right? We have the two conditions. So that is about if and only if. So we have the abbreviation here. It means, right? You should be familiar with this representation, right? IFF is short for if and only if. Okay? Right? Subset, okay. When A is a subset of B, but A is not equal to B, then it means that A is a proper subset of B. Okay, that is the size of set A is smaller than set B. Okay, we can see that in a Venn diagram here. Right. So that we use this one if A is a proper subset of B, but if and use this one when A is equal to B or B equal to A. Right? The cardinality of a set. Okay, this is another notation that we have to know. Okay, cardinality means size of the set or number of elements in the set. Okay, just like we can see examples here. Empty set. We use the symbol like set A. The cardinality, we use this sign, okay, means cardinality, right? Or size of number of elements in the set. So that if it is a set of empty set, then that means no member. So the size is 0. English alphabet, we have 26 alphabet, so that's the size of the set. Next one, we have 3 elements. This one we have 1 element, okay. See that this and this are not the same set, right? If the set is infinite, okay, meaning that we could not count the number of elements in the set, okay, like they are just like infinite. So that's an infinite set. What else? We have power set, right? Set of all subsets of the set there. So that the number of when we have n elements in the set, then let's see, when n is equal to 2, in this example, considering this set A with 2 members, n is equal to 2. The power set of A would be the all of this, right? Like empty set is one of them, and then one of the members, okay, one or two. So that how many members do we have? 2 to the power of n, right? Is 4. Okay. So that is the cardinality of the power set. Right? But if we have 3 elements, let's say set B consists of elements 1, 2, 3, then what is the cardinality of the power set of B? PB. That would be, we just list all out, right? 1, this is empty set, 2, 3, right? And then 2 of the members, 1, 2, 1, 3, 2, 3. Anything else? One, 2, 3, right? So that would be 8 total. So that the size of this is 8, right? 8 members of the power set. Okay, right. We already discussed about the subset, right? Subset. Okay, proper subset as well, right? We can use Venn diagram to represent that the sets. Okay, they are moving on to the next one, Cartesian products. Starting with the definition, when we have 2 sets A and B, then the Cartesian product of A and B, we represent it this way. Okay. Take a look at this one, like this is set A and this is set B. So that there is a mapping or from A to B. Okay. 1 member here and 1 member here. Right. From A to B. Okay. But from B to A is different. Okay. They are not the same. We can see that from the example. Okay. Set A and B are given. We can find out the Cartesian product of A and B. Right. Selecting 1 member of A and map to 1 members of the B. So here are all of them. Right. But the Cartesian product of B and A is different. Right. The next one. We know that, right? Okay. So the Cartesian products of the sets, okay, we could have multiple sets, like previously, just only A and B, right? 2 sets. If we have n sets, then the Cartesian product would be the mapping, like as shown here, right? 1 member of the first set, the second set, and so on. So that it doesn't matter how many sets do we have, then we can find out the corresponding Cartesian products, like as shown here, when we have 3 sets, right? Then we can list out all the right members here. Okay, so that's about like terminology and notations for the set. Let's move on to the set operations. Okay, set operations. Then this would be very much like the logic that we discussed last week as well, right? We have union, okay, union. So this is like OR. Okay, like OR. Intersection, this is like logic AND. Disjoint, okay, disjoint. A and B have nothing in common, or they are mutually exclusive. Okay. There's no common between A and B. Difference, okay, in A but not in B, right? And complement, so that's the negation, right? Or not. So having the bar on the top or something like that. So Venn diagram can be used, right, to represent all the operations of the set here. Okay, I'm gonna make it. We can, right, skip the detail. Let me know if you have any questions. You can raise your hands. Okay, or we can discuss some more during the break as well. Difference, right? A minus B means like in A but not in B, right? So we could see that the highlighted one here, right? The parts of A that's not in the B set. The AND, okay, we have this is for take a look at when we have 2 sets like this. Okay, we can find out the union and the intersection part and so on, right? We are also familiar with this one, right? Where the A union B is equal to A plus B minus A and B. Okay. Then we have this sign, right? This sign means about the cardinality, the size, so that the answer would be just number, right? Integer, telling how many members in the set based on the operation here. Okay. Let's see this example, right? When A is a set with a number of students in math, okay, math major, and B is a computer science major. We want to find out the number of students who are math or computer science major. So that is A union B. So that we just find out like how many we have in A. Let's say we have A is let's say 40. And let's say if we have B is 50. And there are some students who have both majors, A and B. Let's say 5. So the remaining part would be just straightforward, right? Doing the summation and subtraction. So that would be 85. A union B. That means we have 5 here, we have 35 here, we have 45 here, right? There are 5 students who are both like math major and computer science major. Right? So that A is 40. And then in this slide, we see simple examples for the union, intersection, the difference, and the complement of the set. Right? So that when union, then we just select members from both sets and put here. Right? Only the unique members. The intersection, we just get the members that belong to both sets, right? So that would be the 1 and 3, right? That's it. Difference in A, in the first set, but not in the second set. So that only 5 is what we got here. And this one is only the 2 is what we got. The complement of the set. Right? So let's say set A, complement of the set A bar or not A. We also use this symbol. Okay, see this one? Okay. So you got to be careful about this symbol. Right? It looks like A, but actually it's not A. Okay, just like when we type, it's easy to make it this way, right? Instead of finding like a symbol, putting on the top. So it's like A prime. A prime, that's A bar, or this is not A. When A is a set positive integers greater than 10, okay, then the universal set is positive integers, then the complement of the set would be the positive integers that less than 10, right? Opposite. Not greater than 10, that means less than 10. There are corresponding laws, right? Identity laws, domination law, and so on, okay, for the set operation. Similar to the logic discussed last week, like set operation, A union with empty set, right? Union is mean like or, right? So that is A intersect with a universal set, then we got the A. The result would be just the same as before. That is A. Domination, dominate, means that universal set, okay, when it is union with any set, the result would be just the whole thing, universal set, right? Empty set intersect with any set, the result would be empty set. So it's just like AND, right? AND operation. Next one, right? When we have A union A is A. Similar to the logic, like A or A is A. Right? A and A is A. Complementary. Okay. So this is a double, right? Just like double negation. Not of not A is A. And these are the laws, okay, for the set operation, right here. Very much about the logic that we discussed last week. And then we also could use truth table again to prove or disprove the given statement, right? The set operation here. We have A, B, and C, right? Okay, all right. Let's take a look at this example. We want to prove that the given operation at the left-hand side is the same as at the right-hand side. Okay. Using the laws, okay, the laws there. See that this is a complement, okay, complement here and also here. So we got to be careful. The left-hand side is the same as when we write it this way, A union B intersect C. And we put the bar on the top of the whole thing. Right, put bar on the top. So with the De Morgan, okay, this is to consider like we have two parts, union of the two parts. Okay, the two parts are A, and inside the parenthesis C intersect with A, B, and C here. So with the De Morgan, we just split the bar for A and for the other part, and then change the operation from union to intersection. Right? That's how it works. Right? And after that, we work on the group inside the parentheses. Right? this part. So that is B. This one. Right. With De Morgan, we split the bar for B and for C, and then change the operation from union to intersection or intersection to union. So that's what we got here. Right. We can, with the commutative law, we can swap the positions here, so that just like x and y, or x or y. X or y is the same as y or x, right? X and y, okay. It's the same as y and x, right? Union or intersection. Mm-hmm. Hold on. Okay. Looks like there is a typo here. Can you see that somewhere? This one, right? There is no bar. This one should be removed. Mm-hmm. Okay, so by doing this, we can prove, okay, or disprove the given statement or operation, right? Or we can use Venn diagram to do that too. Okay, let's move on to the next section, which is about functions. Functions. We are still considering sets A. Okay, we have, let's say, A and B are sets. Function F from A to B, right, a mapping or assignment. So that exactly one element of B is mapped to one element of A. Okay. So that here is a domain, right? Domain. And this one is the codomain. Okay. Mm-hmm. Exactly one element. Okay, let me move to the a couple slides ahead to see, okay, in more detail, okay, about a function. So this is like set A, and this is set B, like this. Okay, why this is not a set? This is not a function. If there is a mapping from A to B like this, because based on the definition, okay, exactly one element of B for each element of A, right? So just like here, this is from A to B. But if we have more than one, like this way, okay, another element of B also mapped to A, this is not a function. right? So that's the reason that this is not a function. But the other cases shown here are functions. Only one element of B is mapped to A. Right? The function, there are many types, as you remember, like one-to-one function. One-to-one, 1:1 in Thai, right? So that means one element of A mapped to one element of B. And then the next element of A mapped to a different element of B that haven't been mapped previously. So this is the case, one-to-one, right? One-to-one. This also one-to-one. Sometimes we could have not one-to-one. Here that, see this one, right? This case. C maps to 2, and D dog also maps to 2. So this is not one-to-one, right? But still a function. What else? Not on-to. Okay. On-to or not on-to function. To be on-to function means that all elements of the codomain B, right, are mapped, are used in the function. Otherwise, we have the not onto, right? Because here, this case, we see that the element 3 is not mapped. Okay. There is no assignment from an element in A to the 3 element in B, to this element in B. Okay. This is not onto because this element, number 4, is not used. Right? So that's why we could have many different types of function as shown here, one-to-one and onto, one-to-one but not onto, not one-to-one, not onto. Just, any of this. Right? These are the properties or the types of the functions discussed here are here. In this definition, like one-to-one. It is also called injective. Onto, that is surjective. One-to-one and onto, that means bijective. That means both, right? Both. Okay. We could do arithmetic operations for the set as well. The function. We talk about function for now, right? Considering like 2 functions, okay, F1 and F2, like this. So this is a arithmetic operation, like F1 plus F2, F1 times F2. Just directly apply, right, the summation of what we have here for F1 and for the second function. So that is just straightforward, right? And also for the multiplication, F1 times F2. Okay. So given some like functions, we can identify if they are exactly the function, actually functions, or not. Okay. If they are functions, then what type are they? Right? Case number 1, fx is equal to plus or minus x. This violates the requirement for a function, right? That is, the codomain, the fx, could be just only one value for any x, right? So that we could not have two possible values for the function. So that's why this is not a function. The second case, function fx is equal to the absolute value of x. Absolute value, that means a positive or non-negative number, right, as a result. So just like it is a function, like if f of minus 5, that would be equal to 5, right? And equal to f of 5 as well. So x could be minus 5 or positive 5. So that this is not a one-to-one function. The next one, similarly, if x's could be positive or negative, right? Just like minus 3. Then this is 9, same as when x is positive number 3. So this is not a one-to-one function. But the next case, it is, right? F of minus 3 is equal to y, the f of 3 is 27. So that's why it is a one-to-one function, right? The value of the function, positive or negative, would be just exactly the same of the x value. If x is positive, the function is positive. If x is negative, the function is negative, right? Okay. And the last case is just a one-to-one, right? X plus 3. Okay. So that there would be some exercise problems for you to work on, okay, related to this. Okay, and then we have what else about inverse of the function. Function f, inverse of the function is this one. When f is a function from a to b, the inverse would be the other way around. It's a function from b to a, right? So that here would be changed to be y, and this would be x. When the function is this one. Okay. We can see the mapping is just backward, right? From the diagram here, first we have a mapping from set A to set B as a function f, right? From the left-hand side to the right-hand side. And the f inverse would be backward from the right-hand side to the left-hand side. Right. Show in more detail here. Another one is a composite, okay, composition, meaning that when we have multiple functions, okay, we have function f and function g, let's say, then the composition of f with g is represented this way, FOG, okay, FOG. So let's take a look at the diagram here. Then we have a function from A to B, okay, from set A to set B, that's a function G, okay, G. Okay. And after that we have function F, okay, mapping. So that got to do this one first, right? Gx function, and then fx would be after that. So that's about FOG. But if we have GOF, okay, GOF, X. This is not the same as FOG. Right? Because this one would be G, F, X. Okay, we can see that in the following example here. Suppose function f and g are given here. So this one is the result, and this one we have a different result. Okay. So you must know the difference. Right? Okay. The next one is about some more important functions for an ceiling function. Okay. Or maybe you are more familiar with the term like upper bound and lower bound. Okay. Considering the four function, okay, or the lower bound function, okay, fx, when x is a real number. Then this one, right, for function, the result would be integer, right? Integer. Largest integer less than or equal to x. So let's take a look at this case, okay, when x is equal to 3.5, then the floor function is 3. But if x is a negative number, then the result, got to be careful on this one. Okay, the result is not -1, right? But -2. Okay, why? We have to think of this one, okay, the line here. Okay, take a look at the left-hand side, like a graph here for the floor function. This one should be y equal to, okay, this one, okay, the floor function. When x, considering this one, okay, this one, okay, let's say when x is less than 2, 1. Okay, that's what it means. Like we have a closed interval here and open interval here. X is less than 2 and x is greater than 1. So applying the for function, the result would be the largest integer that is less than or equal to x. So it's this one. So it is 1. Right? This is the same when x is like the other case here. Right? So that's about the floor function. So the result would be so for any x, the result would be just here. Shown here, that's the result of the floor function. Right? The largest integer that is less than or equal to x. Okay. So this is when x is like between 2 and 3, and this is x between 1 and 2, or and so on. But for the ceiling function, the result would be opposite. Okay, that is, the result is the smallest integer. That is greater than or equal to x, right? Okay, let me go back to the definition here. The ceiling function, we use this sign. The result is integer again, but it is a smallest, okay, smallest integer greater than or equal to x. Right? So ceiling function, this one, the result is 4. And if we are dealing with a negative value, then it's this one. Okay, you just look at the sign. Like when x is -1 minus 5, where is it? It could be around here. Okay, x could be somewhere here. This is x. Right? So that with the ceiling function, the result would be just this point here. This is the value. Right? minus 1. Okay. Because minus 1 is greater than minus 2, right? Okay. You should also check out this table, okay, to make sure that you agree with all these properties. For both the floor and the ceiling functions. Okay. Then what else do we have here? We have about sequences and summation. Let me cover briefly this section, and then we take a break and we come back to work on the exercise problems. Okay? The sequences and summation, we already familiar with like the sequences like AN. Or like if AN is equal to 4 to the power of n or something like this, right? We just plug in the number n. N is 1, 2, 3, and so on. Then we find out the corresponding values as a sequence. The well-known sequences are here. N squared, n cubed, and so on. 2 to the power of n factorial. There are two main sequences that we know, right? One is called the arithmetic, sequence. The other one is a geometric sequence. The arithmetic sequence should be like this. Like we add just a certain value, then we obtain the next value in the sequence. But for the geometric, then it has to do with not addition, but multiplication there, right here. Okay. A well-known sequence is Fibonacci sequence. Anyone is familiar with this one? Let me see your hands. Fibonacci sequence. Okay, that's good. Which is this one, right? So the sequence Fn, or we can think of that as a like function. When we know the initial condition, that is the F0, okay? F0 and F1 are known. Then we can find out the F2, F3, and so on, like here. Okay, given F1 is 1 and F2 is 0, then we can find out F2, F3, and so on. Okay, this table shows the well-known useful sequences. summation. Summation is just about addition, right? This sigma, a Greek symbol, represents the summation. Summation of the AJ, where J starts at M, minimum is M, and at most N. So J is incremented, okay, by 1, so that we will have the first term is AM, second term is AM plus 1 up to AN, summation, right? Sum of AJ. Okay, let's find out the summation of J square, where J is from 1 up to 4. What is the result? J start from 1, so we have 1 square. When J is 2, we have next term. Just that, right? Summation. So that there are 4 terms. When J is 1, J is 2, J is 3, and J is 4. And just work out the numbers. Is that 30? Okay. If we have J is from 1 up to 5, then we have additional term here that we can do similar to the previous one that we obtained. Okay, which is just that. So it's 30 plus 25, 55, right? This is equivalent to another summation of k plus 1, total square. So k is from 0 up to 4. The next example, we have the double summation. So how to do that? We just work on one summation at a time. Okay, like inside is a summation. J start from 1 up to 3. So what is this? So I is we just leave it. So we have like I plus, when J is 2, so we have 2I, 3I, right? So that's equal to 6I. And we can take 6 in front as a constant. Can we? Hold on. Summation. Let's try that. I is from 1 up to 4. So we have 6. 1, 2, 3, 4. 60. Right? What about if we consider the summation? We can check 6i. I is from 1 to 4. Right? 6i. They're the same thing. Okay, so when we have double summation, something like this is how it works. Okay, finding out the value. There are also closed form of the summation, like that you have seen, like some of them previously, right? This one, summation of k. K is from 1 up to n as this form. When k square is this one, k cube is the other one. Okay, the other one. Or this. Okay. Similar to summation, that is not about products. Okay, products. So it has to do with multiplication. The sign here, a Greek sign like a pi. Is that this one? I. Let's say J. Okay. Product of J. J is from, let's say, 2 to 4. Product. So that would be J2 times 3 times 4. Okay, so the way it works is similar to what we do for the summation, but instead of the addition, right? It's a product multiplication. That's all. That you will see that in the exercise problem too. Okay, all right. So I like to stop here. Okay, before everyone go to sleep. Then we take a break, 10 minutes. And then we're back for the exercise problems. Some of you may almost done with that. That's okay. You don't really have to finish them all today. Okay, you have time. Do some in class to make sure that we understand how to solve them, and then finish them later on. That's okay.